Kusangpo to all the viewers. Welcome to physics lesson T stage 5. I am Norbo Wangdi, teacher of Gongsam Ukendoji Central School. In today's lesson, we are going to discuss about electron diffraction and hydrogen spectrum. Before we proceed into the actual lesson, let me tell you what things you should know at the end of this lesson. First, you should be able to explain the electron diffraction. Secondly, you should be able to explain spectrum, different types of spectrum as continuous spectrum, line emission spectrum, and line absorption spectrum. Explain the formation of hydrogen spectrum and calculate the energy when electrons transit from one energy level to another energy level. With this, let us recall the lesson that we know on light. As we all know that light behaves in two ways, therefore it has got two characteristics. Because of that two characteristics, we say that light has a dual nature. Scientists discovered that light behaves like waves, and it was proved or discovered by Sir Thomas Young in 1801. In an experiment, he proved that light behaves as waves. And until 1904, people believed that light behaves as waves, unless
Sir Albert Einstein
in 1905, in his photoelectric experiment, he discovered that besides waves, light acting as a waves, it is also behaving like a particle. Therefore, we conclude that light behaves like particles as well as waves. In today's class, we are going to learn that electrons also behaves like waves, meaning it behaves like particles as well as waves. And this demonstrates how electrons behave like waves. With regard to particles of electrons, we know that electrons are the subatomic particles that we have already learned in lower classes. Now, let's look at how electrons behaves like waves. The idea behind the wave nature of electron was proposed by Sir de Broglie in 1924. He proposed that electrons undergo diffraction. It means that electrons also behaves like a waves, because only waves will undergo diffraction. Now, let's look at how Sir de Broglie conducted the experiment in 1924. Now, if we look at this diagram or representation, I have a closed glass tube. It's commonly known as hot cathode ray tube, and this part is called electron gun. And we have a hot cathode here, which is connected to potential difference, and I have the ring here, which is used to focus the electrons, which is being accelerated by the hot cathode towards the target graphite. And we should know that graphite target is made up of carbon atoms, which is arranged in crystal lattice. And we have last, at the end of this cathode ray tube, we have the screen. Now let me explain how it works and how Sir de Broglie proved that electrons are behaving like waves. Now, when the potential difference is applied from here, the cathode is being heated up. When cathodes are being heated up, it emits the electrons. The emitted electrons are accelerated towards the target by accelerating anodes. And after heating target, it's observed that on the screen, concentric rings of dark fringes and white fringes are seen. If electrons behaves like particles, there should be scattered patterns on the screen. However, instead of scattered patterns, concentric ring of interference, both destructive and constructive interference, is seen on the screen. So through this experiment, this is how Sir de Broglie proved that electrons undergo diffraction. Therefore, it possesses the nature of waves. Since electrons behaves like waves, we can calculate the wavelength, which is denoted by symbol lambda, by using the formula lambda is equal to h by p, where h is the Planck's constant and p is the moment of individual electrons. And we know that momentum of any moving objects can be calculated by multiplying mass and velocity. Therefore, we have p is equal to mv. After studying about electron diffraction, now you may wonder, where do we apply? Here I have listed few applications of electron diffraction. Number one, electron diffraction is applied in the study of solid crystal structures. Secondly, electron diffraction is applied even in medicines, in making medicines with crystal structures. Thirdly, electron diffraction is applied in study of biological specimens. Now the next topic is about hydrogen spectrum. Before we start with hydrogen spectrum, let me introduce you with three types of spectrum. And you are very much familiar with one of the spectrum, that is called continuous spectrum. Continuous spectrum is produced when the hot objects gives off all the colors of wavelength. For instance, the spectrum produced by sunlight is called continuous spectrum. The other type of spectrum is called emission line spectrum. And emission line spectrum is produced by hot objects when they give off particular color of wavelength. For instance, scientists discovered that some of the stars and galaxies, they produce emission line spectrum. The third type of spectrum that we have is absorption line spectrum, produced when atoms of hot objects absorb certain colors of light. For instance, hydrogen gas, when heated to high temperature, it produces absorption line spectrum. And now we are going to look at how hydrogen spectrum is produced. In order to produce hydrogen spectrum, these are the apparatus that we required: closed glass container, glass tube, prism, and heat energy. These apparatus are arranged in this way. The glass tube is attached to glass container, and opening of the glass tube is placed near the prism. Now let me explain the production of hydrogen spectrum. When external heat energy is supplied, the electrons in the hydrogen gas, they get excited and they start to transit from one energy level to another energy level. And during this transition of electrons, they will absorb or release energy in the form of photons. And if we make that photons to strike on the prism, it undergoes refraction. And due to the refraction of that photons, absorption line spectrum is produced. This is how hydrogen gas produce absorption line spectrum. In order to make the concept clear, let us again look at how the change of energy takes place when electrons transit from one energy level to another energy level. Here I have this atomic structure of hydrogen, and in the center we have nucleus, then first energy level, second energy level, third, and it goes on. And we call first ring as energy level 1, n is equal to 1, followed by n is equal to 2, then it goes on. Now, it's said that when electrons transit from higher energy level to lower energy level, that is to the lowest energy level, that is n is equal to 1, a spectrum called Lamar series is produced. In the same way, when electrons from higher energy level transit to second lowest energy level, hydrogen spectrum called Balmer series is produced. Similarly, when the electrons from higher energy level transit to third lowest energy level, a series called Paschen series is obtained, and that Paschen series lies in infrared region. Likewise, when electrons transit from higher energy level to fourth energy level, a series called bracket series is produced in hydrogen spectrum. Now let's look at the position of Lamar, Balmer, Paschen and bracket series. As I told you earlier that Lamar series lies in ultraviolet region, so therefore Lamar series is not visible to our eyes. Balmer series, it lies in visible region, whereas Paschen series and bracket series, they lie in infrared radiation. Also, Paschen series and bracket series is not visible to our eyes. Okay, now with the help of these simulations, let us see how energy changes when electrons transit from higher level to lower level and from lower energy level to higher energy level.
Now, in order to understand the concept clearly, let us look at this simulation. And this is a simulation for hydrogen atom and its energy level. So as you can see very clearly on the screen, you will see that hydrogen atom with its energy levels. So this is the first energy level or the ground state where it has minimum energy, and this is also represented or shown as n is equal to 1. And subsequently, as you move out or move above this, the other rings shows that n is equal to 2, n is equal to 3, n is equal to 4 till n is equal to 7. And as electron transit from lower energy, that is ground state, to high energy level, there is absorption of energy taking place, and as electron transit from higher energy level to lower energy level, there is emission of energy taking place. So at the side line, these lines also represents the energy level. So in the ground state, when electron has an energy of negative 13.6 electron volt, it is shown here. And you can also see that there's a huge gap between the first energy level, that's ground state, to n is equal to 2, which means to say that tremendous amount of energy is required to transit electron from ground state to n is equal to 2. And as you move up the series, you will see that the gap are reducing, meaning not much of energy is required to emit or transit electron in the high state. So in order to get the clear picture, let us look at how electron transit from one energy level to another energy level. So that is, when electron transit from first energy level to when n is equal to 6. So you can see clearly from the diagram here, when electron transit from n is equal to 1 to n is equal to 6, that is from ground state with energy negative 13.6 electron volt to n is equal to 6 level, that is energy level or amount of energy as shown here. So you'll see that photon is being absorbed. Simultaneously, we can also see from this tabular representation that when electron transfer from n is equal to 1 to n is equal to 6, that is energy possessed at initial position when n is equal to 1 is negative 13.6 electron volt, and energy possessed at final state, that is when n is equal to 6, is negative 0.378. So applying or using the formula, the change in energy, that is initial energy minus final energy, that is negative 13.22, and the remarks, as you can see here, energy is being absorbed. Let us look at when electron transit from first energy level to fifth level when n is equal to 5. So you'll see that the amount of energy, since it is going from lower energy state to higher energy state, again energy is absorbed, or photon is being absorbed, and the change in energy, as you can see, when it transit from n is equal to 1 to n is equal to 5, that is from lower energy level to higher energy level, the change in energy is negative 13.06. So here also the energy is being absorbed. Now let us look at how it is happening, how energy transfer is taking place, or whether energy is being absorbed or released when it transfers from higher energy level to lower energy level. So let us consider n is equal to 6, electron transit from n is equal to 6 to n is equal to 1. So in that case, when electron transit from n is equal to 6 to n is equal to 1, that is from higher energy state, which is negative 0.378 electron volt, to lower state, lower energy level, that is negative 13.6 electron volts. So you will see that when it transit from higher energy level to lower energy level, you will see that the change in energy is 13.222. So in that case, the energy is released. So looking at our simulation, you can also see that the photon is being emitted. Let us look at when electron transit from n is equal to 5 to 1. So in this case, also you will see that since electron transit is taking place from higher energy level to lower energy level, from n is equal to 5 to n is equal to 1, that is ground state, you will see that change in energy is again positive, which means that energy is being released when electron transit takes place from higher energy level to lower energy level. So photon is emitted. So from this simulation, what we can conclude is when electron transit from lower energy level to higher energy level, photon absorption is taking place and energy is being absorbed. And when electron transit from higher energy level to lower energy level, a photon is being emitted, or in other words, energy is being released.
In the video, you have seen that when electrons transit from lower energy level to higher energy level, it absorbs energy in the form of photons. Similarly, when electrons transit from higher energy level to lower energy level, it releases energy in the form of photons. Now, how do you calculate it mathematically? Also in the video, we have seen the energy of electrons in its own specific energy level, and as well as the differences of energy in different energy levels. But how do we calculate it mathematically? We can calculate the energy of photons absorbed or released by using this formula. I have here E photon is equal to EI, which is energy level of electrons in its initial position, and EF is energy of electron in its final position, and that difference in energy is equal to HF, where H is Planck's constant and F is frequency of the photons. We can replace this EI minus EF as delta E, because delta refers to difference in energy. Therefore, we have delta E is equal to HF, where F is frequency, and we know that frequency is equal to velocity over lambda. However, in case of hydrogen atom, to find or to calculate the energy of electron at a particular level, that is for n level, we can apply this formula. En, where E is the energy, n is the energy level, is equal to 13.6 Z square over n square EV, where Z is atomic number and n is the energy level. As we have seen in the video, we have seen that energy level of electron in the first state, that is ground state, when n is equal to 1, is 13.6. Let us substitute the value and see whether we are getting negative 13.6 electron volts or not. Okay. Let us substitute here 13.6 times 1 square, because atomic number of hydrogen is 1, over or divided by n, ground state is equal to 1. Therefore, 1 square is 1. So, if we calculate the energy of hydrogen electron at the ground state, we are exactly getting negative 13.6, which is also proved through simulations, as we have watched in the video. From the calculations, we got that energy level of electron in ground state is equal to negative 13.6 electron volts. Since electron volt is a unit of subatomic particles, let us convert that electron volts into joules, because SI unit of energy is joules. To understand the relationship between electron volts and joules, it is a bit easy. We can just say that 1 electron volt is equal to 1.6 times 10 raised to minus 19 joules. Now I have one question for you, and let us solve this question together. The question is, how much energy is released when an electron transits from orbit level 4 to 2 in hydrogen? The solution we have is, and in this question the given things are, first we have the initial position of electron, that is equal to Ni, which is equal to 4, and final position of electron is equal to 2. And particularly for oxygen, we know that atomic number is equal to 1. Therefore, we can simply substitute Z by 1. Also, if we recollect the formula that we have learned earlier, that En is equal to minus 13.6 Z square. The energy level at particular n level is given by negative 13.6 Z square over n square EV. Therefore, we can find the difference in energy when it has transition is taken place from orbit 4 to 2. Substituting the values, we have negative 13.6 Z square over Ni square minus negative 13.6 Z square over Nf square EV. Now let's substitute the values. We have negative 13.6 times Z square is 1 square and Ni square is 4 square, because initial position of electron is at 4, whole minus negative 13.6 times again Z square, 1 square is 1, and Nf is final position or energy level of hydrogen, which is 2 square, whole bracket close times. Now we are converting that electron volts into joules. Therefore, we are multiplying 1.6 times 10 raised to minus 19. And if we simplify these operations by using calculator, we will exactly get positive 4.08 times 10 raised to minus 19 joules. The answer is positive 4.08 times 10 raised to minus 19 joules is the energy which is released by electron when it transits from orbit level 4 to orbit level 2. It means transition is taking place from high level energy to lower level energy. That's why energy is being released. After we have learned about hydrogen spectrum, you must be wondering, where do we apply the knowledge of hydrogen spectrum? I have listed few applications of hydrogen spectrum. Here I have listed a few applications of hydrogen spectrum. Hydrogen spectrum is used to study redshift. In physics, we have learned that this universe is always expanding and it's always in motion. And the expansion of universe is proved when the light is shifting towards red. Another application of hydrogen spectrum is it is also used in astronomy to check the presence of hydrogen atoms. Now we are almost done with the lesson. Let us recollect. First one is we have learned that electrons behaves like particles and as well as waves. Therefore, electrons undergo diffraction. And then we have also learned that diffraction of electrons are used to study the crystalline structure solids. We have learned about types of spectrum. They are known as continuous spectrum, emission line spectrum, and absorption line spectrum. After that, we have learned how hydrogen spectrum is produced. And we have concluded that hydrogen spectrum consists of Lamar series, Balmer series, Paston series, Brackett series, and P1 series. But this is not the end. To end up our lesson, I have tasks for you. First task is explore some applications of electron diffraction. And the second task for you is, if you observe sun's spectrum with a high resolution spectrometer, what kind of spectrum will you observe? Third, calculate the wavelength of radiation emitted when hydrogen atom transits from state n is equal to 5 to the state n is equal to 2. The last task for you. We usually see spectrum around the sun during bright sunny day. Write the belief about the existence of a spectrum around the sun after consulting with your parents or community. Thank you for spending your valuable time with me, and I hope you have enjoyed the lesson. See you in the next lesson.